Okay, let's get formally started. And so today, let's go through the history problem first. Is that, this is one of the problem proposed in the chat. And to review, for this type of problem, basically, I'm still going to do it in 3 ways. So basically, it's kind of a discrete counting. And if it's a 40 probably 40% of the chance it's going to rain, you actually could do it in 3 ways. And if you do it in counting way, basically you are saying that for each day, you have 2 choice, rain 1 and rain 2, and then you have sun 1, sun 2, and sun 3. So basically, for each day, you can use a discrete letter arrangement to simulate like 40%. Then because so this is actually repeated counting, and for a week is 7 days, and what we are seeking is that a rain will be on 3 position and the sun will be on the rest of 4 position. So this is what we are doing. So what we are trying to count is like a 7 tuple. So basically 7 tuple. And this problem actually is easier to do use the probability way, but I just want to show you all the ways. So let's say that if we, so 3 way, 1 way is that using the like ordered tuple and ordered tuple. So basically, we have 7 position and 1, 2, 3. And 4, 5, 6, 7. And so if you really imagine, without restriction, so the sample space is that for each position, you are free to choose between those 5 letters. So each position is a 5. And so the second day, you still are free to choose those 5 letters. And you have 7 days. So in the denominator, by order tuple, it's 5 to the 7th power. And then we will trying to choose how many way to arrange those, basically rain in those 7 positions, and 3 of them is rain, and like 4 of them are sunny. And then basically to choose first we need to choose like 1 to 7, choose 3 position to put the rings. And with each letter, basically we will have to choose so 7 through 3 is where we're going to put the rings. And then we actually have to to 5 choose 2. Yeah. Let me cross out this one. This actually, let me just use the probability way. Probability way is actually, this one is much more easier. And So the probability way, if we do the probability way, basically, it's 7. We need to choose 3 days that is the rain. And it's 7 through 3. Then for each of those 3 days, for example, first, second, and third, we actually have to 2/3 to the 3 powers, and the rest of the 4 day actually 2/5 and 3/5 to the 4th power. So that is the way to do it for if we just do it this way. And the simulation basically, yeah, this type of thing, let's forget about simulation. One time I was thinking about the simulation very clearly, and for whatever reason, I kind of went blank right now. But as long as you know one way to do the problem, is still good. And so this one is like, this problem is that we need to choose like 4 stripes, choose color for 4 stripes. So basically what we are going to do is label the stripes. For example, this is 1, 2, 3, 4. And for those stripes, each stripe have free to choose 3 color. So basically red, blue, and green. So each position, you actually got 3 choice. You've had 4 positions, so basically 3 to the 4th is the total choice. Then after you get like those 4 choice, that's the sample space. The sample space, the denominator is this many choice. Then we will trying to see that the way to choose 3 color and none of those colors share the same edge. The only possible way, for example, let me just color it. And this is blue. And those, one is the blue, one is the red, and the other is green. And so if we color it, basically, if we color it, in order for it to not sharing any edge, this is the only way. So one of the color will be on 2 and 4. The other 2 color will share 1, 3. So that's the only possible way to have no color sharing the same edge. So basically, let's say that blue is on 2, 4 positions, and on 1, 3, there are 2 possible ways, either green, red, or red, green. So that's for 1, 3. So basically, it's if we trying to count the ordered tuple, then basically that's going to be like, because we have 3 color, we can rotate 3 color in this 2, 4 position. So 3 multiplied 2. So basically that's going to get like, we can cancel this to be like 27, 227. So that's the way that, how many ways we can do it. And this one is 4 of the vertices of the regular octagon are selected random and connect to form a quadrilateral. What is the probability that the quadrilateral will be a rectangle? So this one actually, first we have to, determine the shape of the data. So for all the vertices, and also like what's the probability that will be rectangle. So we actually is randomly for choosing 4 vertices. Randomly for choosing 4 vertices, And then, looks like the data shape, we use unordered. Unordered set is the easiest one. Unordered set, and those are on like unordered set, and the set is made up of four member. So unordered four member set, that is the best way to describe the data. And without any restriction, the denominator going to be 8 choose 4. 8 choose 4 is the total count without any restriction. Then what we really trying to do is that how many ways we can construct rectangle. And this actually, we can try to pick, this is one way, and we rotate it. We can find out this is the position 1, position 2, position 3, position 4. So this we can rotate. And when rotate to here, then it's going to begin to duplicate. So basically, we actually has 4 position of the long rectangle. Then we also find out it's possible to choose a square. A square is still a type of the rectangle. So this is one way. And this is the other 1, 2, and 3, 4. So basically, so we have 2 rectangle plus 4, or 2 square plus 4 rectangle. So basically, that's the way. It's 6 on the top. 8 choose 3, or 8 choose 4 is 8, 7, 6, 5, and 4, 3, 2, 1. So we kind of get, and 2 multiply 5 equal to 10. So it's 70. 70 on the bottom. So this is 3 multiply 2, and 35 multiply 2. We cancel out 2. So this is the answer. And then this problem is that each of the 6 faces of the cube is painted either white or black with equal probability. What is the probability that 2 black faces share an edge? So this one, basically, it's finding the way how to paint the 6 face. Even it's a symmetric like shape, you still have to label all the faces with number. For example, you have to label it face 1 all the way to face 6. And basically, each face got a chance to pick white or black. So basically, the data structure is like a hexatuple. So the hexatuple made up of 2 letters. You are free to choose 2 letters, either black or white. So because you have 6 positions, and each position you are free to choose 2 colors, so the denominator going to be 2 to the 6th power. And then what we are trying to do, see what is the favorable. So no 2 black face share an edge. And what we find is that, if we trying to paint this side black, then there are 4 adjacent sides cannot be painted black. The only thing can paint black is right at the opposite. So the opposite can paint black. So basically, at most, you can have 2 black side, black face. If you have more than 2 black face, it's guaranteed to, have some face share at least one side. So what we're trying to count is to count the cases with 2 or less faces. And then, if you have 2 or less black faces, if you have 0 black face, if you have 0 black face, it means all white. It's all white cube. All white cube basically don't have this problem because it have no black face at all, and it don't have 2 black face sharing a side problem. So it's a working favorable case. Here we need to count in. And then if we have just one black face, if we have one black face, and it's still favorable because there's no other black face for it to share the edge, it's all working cases. And how many cases do we have? Because we have 6 face in the total in this cube. We are free to choose which face is black. So we have 6 choice. So basically plus 6. Then we will think about like 2 faces black. 2 faces black, we have 3 ways to do that. We cannot do 2 adjacent black, so we have to list them, enumerate them. And so, two-face black, if we use, because we are counting the unordered tuple, so basically if you really, do it, it's going to be 6 multiply 5 divide by 2 and it's a lot. But because only the opposite side will work, so no matter how you label it, you will know that it's the front, back, left, right, top, bottom. So basically you have 3 case. These are the working case. And those made up of 3 tuple out of this. So on the top going to be 10, on the bottom going to be 64. So we got 2 multiply 5 over 2 multiply 32, and then we cancel that out, equal to 5 over 32. So that's the that is the total way. Yeah. Okay, so the last time I actually, basically didn't explain this clearly. So let me use the, so this problem, I think about it. And so right now trying to do a better explanation. Let me try to stop sharing and just show the video. I didn't get it right, so I think I will try to do it the next time. I will try to do it, and so let me go back to this again. Let me see if I can figure this out, because this type of problem do have 3 ways. So let me see if I go out of blank and the mode, and so sometimes when you do math, it's just like that. It's just trial and fail, trial and fail, fail and try. But it's normal. Just don't get frustrated. And so I know that the final, so what we are trying to count, that if we simulate the whole thing like those things, so basically, each position could be like, it could be R1, and this is R2. R1, R2 is just trying to simulate like 40%, like 40% chance. And this could be R1 again. Then this could be S1, S1, S2, and yeah, S3. So basically it could be this way. And so 7 through 3, then basically, yeah, each position we actually is allowed to choose. So this 3 positions are allowed to choose either rank 1 and rank 2. So basically it's allowed to like 2 to the, because it's 2 to the third, 2 to the third here. This is actually is the multiply 1, 2, 3, 4. That each position is 3 because we have 3 sunny. So 3 to the 4th. So basically it should be arranged like this way. Yeah, if arranged this way, then basically it's still going to be the same as this. So basically, it's possible to do this as a like order tuple, and order tuple usually is always guaranteed to be right in any discrete counting, and then unordered set. Unordered set. Let's see if that's possible. Order set actually it's not possible because the order does matter. So basically, in this case, we actually have two way of doing it, and so that's the that's okay. Because I didn't figure out how to share the screen. Next time, I'm going to, before I share screen, I'm going to show, this is the way. Basically, in this is the old problem is that, I'm showing it to I don't know how you expand because I'm here on the Zoom. If you are able to see this is a tetrahedron, and then basically the way is that this tetrahedron, you have 4 faces. You are able to put down any of the 4 faces down to the table. Then after you put down 1 face on the table, you have 3 ways to rotate on the table. So basically, the multiplicity or to put this on the table is 12 because it's 4 multiplied 3. 4 ways to put a tray, put a face, and 3 ways to spin it into the position. So basically, for any arrangement, for example, for example, you have like 4 divided by or 4 factorial to arrange the 1, 2, 3, 4 face but since you have like 12 duplicity, 12 multiplicity, so basically in reality, this is only 2 way. In reality, this is only 2 way to arrange the tetrahedron dots if you are faced with this situation. So basically, for this, its multiplicity is 2. Okay, anyway, let's kind of continue on to the new topic. And so we are on to the more complementary counting and probability. And this actually was used a lot in the the weather prediction. Did I study recording? I may not even study recording. Let me see. Pause recording. Yeah, I already started recording. So the chance of the rain for each of the next 5 days is 25. What is the probability that it will rain at least once in the next 5 days? So the easiest thing to think about this type of the problem is that just think in 1 day at a time. So just for 1 day, for the next day, and you have 1/4 of chance to rain and 3/4 of chance to no rain. And so then you can think about 2 days. 2 days in a row. 2 days in a row. So basically the first day, you have 1/4 chance of the rain. So this is one day is just, 1, 25%, 75%. Then 2 day, then 2 day in a row, if it's rain, it's 1/4 might multiply 1/4. That's 2 day rain. And then we can have 1 day rain. So it's 1 day rain. The first day rain, the second day sunny going to be look like this. And the first, so this is rain, shine, and then 2 day rain, then sunny and rain, that's going to be 3/4 and 1/4. Then 2 day sunny going to be 3/4 and 3/4. So in 2 day, it's still easy to arrange. So to count, it will rain at least 1 day. In the next 1 day is actually you can also do it 1 minus 2/4, 3/4. And at least 1 day rain, it's actually included all those 3 cases. So you actually can count this way, or you can just 1 minus 3/4 square. So this is actually a much easier way to count, just from 1 day and 2 day. And when you getting into the 3 day, basically you can have so many possibilities. You can have 3 day rain, 2 day rain, and 1 day rain. If you count positively from ground up, it's just already became a nightmare, and you cannot imagine all the way to like 5 day. It's going to be really bad. But 3 day, if you just count no rain day, it's very easy. It's just 3/4 and 3/4 and the 3/4. That's the 3 day sunny probability. You just 1 minus that. So basically, this type of the problem, you may not, feel comfortable doing it first, then, but basically after you begin to do this, then it's became easier. It's going to be on the 5th day, it's going to be 1 minus like 3/4 to the 5th using the probability. And this type of the problem, because it's actually, it's actually an integer thing. So you actually is able to simulate the whole thing with a letter. For example, you can say that rain is just rain, and no rain, you can say sunny, you can say S1, S2, and S3. So basically, if you don't use the probability to do it this way, you still can use the counting. So counting is just another way that, so counting is a 5 day, and 5 days. So basically, it's a 5 day. It's a pentatuple. So it's a 5-tuple thing you are trying to count. And each day, you are free to choose any of those. So basically, you are free to choose rain or sun 1, sun 2, sun 3 to simulate this 25% of the rain, chance of the rain. So 5-tuple basically is like, because each day you have 4 tries, that's 4 to the 5th power. And then basically, you want to get no rain day. No rain day, basically, you have to choose from this space. So basically, it's still going to be 3 to the 5th. Those are no rain days. And no rain days probability using the tuple. And then with at least one day, then it's 1 minus this. So basically, using the ladder simulation, using the tuple, it's going to arrive exactly the same probability as using the probability directly. Oh, someone is knocking. Yeah, so basically, this is the complementary counting. Complementary counting, the quintessential meaning of this is just, you kind of do some little experiment, especially starting from the smaller, simpler case. You find that you find something never changes. You find invariable part. Invariable part is the no rain. To count the no rain probability, it's always just 2, 3 false powers. And if you count rain at least one day probability, it's just starting from 1, it's the equal complexity. But starting from 2, it's just go astronomically more difficult. So basically, you will just focusing on the easy part to do the counting. And this type of problem, complementary, you usually always is a keyword. The keyword you are looking for is that at least. So at least is the keyword you are looking for the complementary counting. It's almost guaranteed. It's always at least. And so let's try to do the next problem. Is that you hold the Q in a game of scramble and need a U to make a word. There are 6 letters left in the bag and 2 are used. If you select 4 letters at random, what is the probability that you will get at least 1 U? So basically, you already hold a Q. You already Q usually has to make word with U. This Q is just something already in your hand, have no contribution. Or make sense is you need a U, and you have 9 letter left in the bag to U. So basically, the 9 letter you can label it this way: U1, U2, and then the 7 letter are non-U. You can label it letter 1, letter 2, all the way to letter 7. And if you choose 4 letter at random, what is the probability you will get at least 1 U? And so basically, looks like you can use tuple or you can use unordered set in there, or you can use probability. So this problem, you actually have 3 ways to do it, I believe. And then we are all going to use the complementary. In either 3 way, we're going to use the complementary. So let's do it in 3 way. So let's say that use order tuple, basically, what we are trying to choose is to choose 4 letter at random. 4 letter at random, so the data shape is quadruple. We are choosing a quadruple. A quadruple is just ordered 4 letter. So choosing a quadruple out of 4 letter or out of 9 letter basically is 9 permute 4. That's the denominator. And the numerator, basically, numerator is like we need to choose at least 1 U. Is actually very hard to do. It's actually more easy to do is that with no U. With no U, basically, we have 7 letters to choose from. And so it's 9. It's not 9, it's actually 7 permute 4. So basically, it's 1 minus this. It's going to work out. Then you can also treat it as an ordered set. An ordered set basically, it's still 1 minus. Then on the denominator, it's just going to be like 9 choose 4. And on the numerator, it's going to be 7 choose 4. So the result going to be exactly the same. So because the difference and 9 permute 4 is 9 choose 4, and basically 9 permute 4 equal to 9 choose 4 and multiply 4 factorial. So basically it's just, this basically is this side multiply 4 factorial on both numerator and denominator. And so that's the way that you can do this problem. And if you use the probability, then you still can do it, because using the probability, basically we are not going to choose any u. Basically, you going to set out to choose 4 letter. So the first letter going to be non-u letter. The way to choose non-u letter is 7 9ths. You have 7, because you're going to break this down into a 4-step action, and the first letter to choose non-u letter is 7 out of 9ths. Then the second step is going to be 6 out of 8ths. Then 5 out of 7ths, and 4 out of 6. Then this is the probability of taking 4 step and not hitting you at all. Then if you 1 minus this going to get. So basically, with either 3 ways, you actually will get the same exact probability. So yeah, so this problem is a little bit interesting. You actually can even build up, because you can actually you can actually use the probability to like choose 2 u, and the rest of them is like 5 other letter. Then you choose just the first u and the 6 of the other letter, and then the second u, the 6 other letter. You can add those probability up to figure this out. So this problem has a lot of paths to the answer, but either way, no matter how you do it, it will be right. So you just have to be confident in whatever path you are choosing. So this one is actually quite easy. So basically, it's 1 minus this. So this is using the probability, and minus the probability. So, but you can do the problem with counting exact, given the exact result. So right now, until this point, it's all like discrete. Basically, every problem we are hitting, if you don't like probability, every one of those problems you are able to solve it with pure counting. Even those ones that, especially even those probability with ratio, like, especially those kind of integer ratio, you always able to simulate them with counting problem and just ignore the probability part at all. But until you hit geometry problem, you have you have to rely on the probability itself, because geometry problem has one of the characteristic is that you can the result is finite. Basically, you can count the favorable result and total result in discrete number. Then the geometry problem, you cannot count those results. You have to calculate the area. So basically, it's a became area problem. For example, this one is that a point is randomly selected on a line, what is the probability that the point will be closer to the middle point of AB? So the middle point is Y, and then closer to middle point, it has to be within this range. And so basically you have 1/2 of the chance. So 1/2 of the chance it's closer to the middle point than further to the, then you also has 1/2 chance, it's further from the middle point than closer to it. Then you will ask, what's the chance of, equal distance from middle point to the end point, You actually has two choices, one X and the Z. So X and the Z is 2, but the favorable count is 2. But the unfavorable count, basically because this is a length or area problem, so the unfavorable count is actually infinity. So basically, you have 0 chance. Even there are 2 points exactly close, equal distance from the middle point to the end point, you actually have 0 chance to land on them. So basically, this is kind of a typical, geometric problem because you cannot count the total result. And so you just have to do it in a geometric way. And so this is another one. And a point is selected at random with a radius of 6. So from here to here is 6. And what is the probability lies in the shaded area outside of the small circle? So small circle is 4. So basically we do this problem just by the total area is pi R is the big R square. And then the ring basically is pi R square minus pi R square. R is this form. So we can actually cancel all the pi, so we don't have to deal with the irrational number. So this is 6 square minus 4 square going to be, this going to be 20, this going to be 36. 4 multiply 5 and 4 multiply 9. So 5 out of 9 going to be the answer. And so let's also see this bus waiting time problem. The bus waiting time problem is that the bus come to a stop near your house at a random time between 6:45 and 6:50. So basically, if you write it on the same timeline, so 6:40 and 6:45 and 6:50, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So basically, your arrival time at the bus station going to be between 6:40 and 45. Then the bus's arrival time is between here and here. So basically, you could wait as long as almost 10 minutes, or you can just catch the bus if you arrive at really close at 6:45 and the bus happened to arrive at the same time. You almost waited 0 0 second. So basically it's going to look like that. It's going to ask you that what's the probability that you're going to wait less than 4 minutes. And if you just lay out the time axis like this, it's extremely difficult to calculate. So a trick in doing the geometry problem is that because those two time, this is your arrival time, this is the bus's arrival time, and those are two different entity, and you can intersect them with like Cartesian coordinate. So basically, it's each axis is labeled with different representing different entity. So here it's for example, this is horizontal axis represent like your arrival time at the bus stop. And then this is the bus arrival time at the bus stop. So basically, if we label it this way, we can also ingeniously like labeling the time scale in a different way. So for here, this is the origin. Origin actually represent, 640 for you. And on the vertical side, it represents 645 for the bus. So basically, this way, this is 640, and so that's 41, 42, 43, 44, and 45. So basically, horizontally, it represents the time that in this style. And vertically, it starts from 645 and just go 46, 47, 48, 49, and 50. So basically, it is labeling the time differently. And when it's labeling the time differently, we magically create the possibility for the arrival versus your arrival versus bus arrival, like probability area. So we created this because, for example, this point represent like you arrive at 45 and the bus arrive at 45, exactly the same time. So your waiting time is 0 for this point. And for example, this point actually represent you arrive at the bus station at 41 and the bus arrive at 45. So you wait exactly for 4 minutes. So that's something we interesting. So we need to find the where is the borderline. So this is the favorable. This is in the favorable area, and this is on the borderline. So 41, 45, 42, 46, 43, 47, 44, 48, 45, 49. So this line is on the borderline. It's actually, this line is the line actually we need to be excluded because it's saying that less than 4 minutes. So basically, this line itself will be excluded. But below this line, for example, I can choose a point to justify my idea. So this is like you arrive at 46 or 43, and the bus arrived at 46. So you actually waited 3 minutes. So this 3 minutes, this is actually waiting for 0 minutes. Then this, you waited even less. This, for example, 44 and 46, you waited for only 2 minutes. So basically, the further away you from this borderline, the less you are going to wait. And right on the borderline, it's you have you have 4-minute wait. And then we can actually draw this. So this square basically representing the total like sample space. So the total sample space is a tuple, is actually a double, like the x coordinate is u, and the y coordinate is actually the bus. So, and so it's a 5x5 area, which encompass all the possible arrival time and of U and bus, and also contain all the possible waiting time. You know, here is almost 0, and here basically, you know, it's almost 10 minutes. So if we put the time around here, it's you arrive at 6:40 and the bus arrive at 6:50. So it's also almost waiting for 10 minutes. So basically this is, so by drawing this way, we actually convert a like a linear thing, very difficult to visual and very difficult to quantify into a two-dimension area problem, which is able to calculate and manage. So the total sample space by area is 5x5 equal 25. And 25 what? 25, I think if you really want to like, you know, give a name, you can like call it like minute square, because both sides is labeled by the minute. And then here, basically not including this line, but everything else is included. And so not including this line, and the area is the 4. So basically it's 1/2 4 multiplied 4, and equal to like 8. So less than 4 minutes. So this is actually, you know, this is the area of less than 4 minutes. So 8/25, that's the answer. And expressing percentage is just equal to 32%. And in area problem, if it asks you exact question, it's guaranteed to be 0. For example, if it's asking the probability, you wait exactly for a minute. Actually, it's 0, because the area of that is just right on this line. And line or dot don't have an area in the in the two-dimension. In the two-dimension, basically line is infinitely small, and or dot is infinitely small, and the line is infinitely thin, so it don't have a width. So basically, you know, it's going to be 0. So usually, you know, if it's like geometry probability, they always ask you like less or greater or equals than, something like that. It won't ask you the problem that, you know, what's the probability that you wait exactly for a minute. And if that's type of the question going to be asked, it's always 0. So let's try to do this problem. And this is the sum less than 4. So what is the probability that two numbers selected at random between 1 and 4 has a sum greater than 4? Express your answer in a common fraction in simplest form. So this is still a two-dimension problem. So basically, you know, if you are given a chance to select two number, and it's between 1 and 4. In this case, you can start from 1, 1, like, label the origin as 1, 1, but I can also start from 0 and 0. If I do that, basically, this is the first number we choose. And so you can, X, you can also say first, the first number. This Y, you can also say second. This is second. The first number we choose going to be between 1 and 4. So I label 1, 2, 3, 4. So it's going to be between here and 1, 2, 3, 4. So the second number is also and 1 and 4. So we actually is able to make out a 3 by 3 square, which will be the sample space of this geometry problem. And we have, sum greater than 4. And so when you work on geometry problem, it's better to treat as a border problem first. Then, not sure what's messing up. Yeah. Are you still able to see my screen? It blacked out for a while. I assume everything's still okay. And so when you have a border problem, greater than whatever, it's actually best to treat it as a border problem first. Then you pick a sample data on both sides to see which side is a favorable one. So sum greater than 4, you basically will try to do this problem as sum equal 4. So this is like sum equal 4. Sum equal 4 basically is x plus y equal to 4. So y going to be equal to 4 minus x. And 4 minus x is just equal to minus x plus 4. So it's going to be a line that going down this way and with the y-intercept 4. So 1, 2, 3, 4. Intercept here going to go down this way. And this is 4, 0, 4, and 1, 3, and 2, 2, and so 3, 1, and 4, 0. So going to be look like this. So on this line, the sum going to be equal to 4. And over there, obviously, sum will be greater than 4. And over here is less than 4. So basically what it's asking the sum greater than 4. Greater than 4, so this will be the area. So this going to be the area. It's actually easy to calculate this area and subtract from it. So this is a triangle. Side is 2 and 2. Side length. So it's 1/2 2 multiplied 2 is equal to 2. And the whole area of this square is 9. So 9 minus 2 over 9 going to be equal to 7 over 9. So that's the, again, this is, always use a greater than, and it never will ask, the probability that sum equal to 4. Equal to 4, that's 0%. And then we are digging into the problem on expected value. And expected value basically, it's just averaging the ideal situation on the average outcome. So basically, this is the simplest problem. That what is the expected value for one row of a standard 6-faced die? And we know that you can, for each dice row, you can get from 1 2, 3, 4, 5, and 6. So in the ideal situation, because it's a fair die, and so if in the most ideal situation that in the first 6 row, you get 1, 2, 3, 4, 5, 6, one of them equally. So then you actually will get a total of 21. If you add them up, you basically it's 21 point. And then divide by 6, going to be 3.5. So basically 3.5 is the expected value for one row, because under ideal situation and on average means that if you do this experiment long enough, for example, do billions and trillions of time, your average point on large number of experiment going to be very close to this ideal situation of 3.5. So that's the expected value. Then we actually have the coin machine problem. And so a change machine is broken if you put a penny, it spit out a coin at random, either a penny, a nickel, a dime, or a quarter, each with equal probability. How much profit can you expect to make by inserting 100 pennies? So this we still, when doing the this type of problem, you still assume the perfection. And so because I have 4 equal chance outcomes, so I will simulate like four coin. So if I insert the first penny, second penny, and the third penny, and the fourth penny. So the first penny is going to turn out 1 penny, and the second penny will turn out 1 nickel. The third penny turn out 1 dime, and the fourth penny turn out a quarter. So this is value is 1, 5, 10, and 25. So basically for 4 penny, if in a perfection situation, this represent all the equal probability outcome, and you actually will add them up, you actually got 41. So basically you are making 37 cents by 4 penny. And 100 penny, it's just like, 25 times, because if you scale up 4 coin by 25 times, you get this. Then profit wide, you will also scale up by 25. So this multiplied 25, we know that 36 multiplied 25 going to be equal to 9. And so 1 multiplied 25 is just adding on to it. So 37 multiplies this going to be like $9.25. And so this one is a we also have a challenge problem. We have a challenge problem is that if the expected value for a coin, if you are allowed to reinsert the pennies that you get back from the coin, what will you get? So basically, if you do this problem, and the answer of this problem basically is a little bit complicated. It's actually simulating into the perfection, and one way, but it actually has the same result if you use a simplified model. Let me just use the simplified model first, and then going to explain the geometric sequence way. And so if you insert one coin into it, if it still come out of penny, then you're going to reinsert it. given enough time you insert it, it could be coming out of penny again. But after, assume you are very bad to, insert 1 million times, still come up with penny. But in the end, you will have good luck enough to turn this penny eventually into one of the 3 other coins. So the journey of each penny until the end of the light going to be turning into nickel, dime, and a quarter. So basically, this is a simplified model. Simplified model basically, the penny, instead of 4 equal chance result, you actually will eventually reach 3 equal chance result. So penny go to nickel, and penny go to dime, or penny go to quarter. So basically, that's going to be 5, 10, and 25. And if you add them together, that's going to be 40. And 40 divided by 3, going to be 13 and 1/3. So 13 and 1/3 is the expected value you're going to get out of this. And the more complicated way which this bucket was taking is that you can assume you are having 64 like coins, like, then after the first round, because there are 4 equal way to come out at penny, nickel, dime, and a quarter. So 16 of them will basically, this 16 of them will turn up to be a penny, and the rest of them going to have like penny. Rest of them going to be 16 multiply 5, 16 multiply 10, 16 multiply 25. Then for those 16, I'm going to do once more. Basically, I will get like 4 of them penny, and 4 of them nickel, 4 of them dime, and 4 of them a quarter. So basically, I will get like 4 multiply 5, 4 multiply 10, 4 multiply 25. Then I have 4 remaining. I do it again. I'm going to get 1 multiply 5 and 1 multiply like 10 and then 1 multiply 25. So basically, you can add them up. Add them up, basically, then you actually have 1. Assume you can split your penny into 1/4 penny. Then basically you can add it became a geometric sequence, which you basically, how many nickel you are getting. Basically, it's 5 multiply 5 is the value of the nickel. It's like 16 multiply or plus 4 plus 1 plus like 1/4. So basically it's kind of something like that. Then the number of the quarter or dime you are getting also is like 10 multiply. This is the same thing, plus 4 and the plus 1 plus whatever. Then this is 25 multiply 16 plus 4 plus 1 and plus all the way. So this became a geometric sequence, and the geometric sequence, so because this part is the same, so we actually can just extract this out. So this add together going to be like 40. 40 multiply 60 plus 4 plus whatever. And so this became a geometric sequence. Geometric sequence, especially, unlimited geometric sequence, we actually has a formula to calculate. It's actually 40 multiply. This is going to be like, for this type of problem, you actually can like multiply. So this you can do it as sum. Then the sum multiply 1/4. The sum multiply 1/4 going to be each term going to be multiply 1/4. It's going to be plus 4 plus, so this is sum, and 1/4 sum basically is equal to this, and plus, for example, 1, this is plus 1, then plus all the way to infinity. Then if you minus it, going to be 16, and the rest of them will be canceled. So 16 equal to s minus 1/4 s. So 16 going to be equal to s, and 1 minus is going to be 4/3. And so s going to be 16 multiply 4/3. So s multiplies 3/4 equal to 16 will be converting to this s equal to, and this result going to be 64, s equal to 64/3. So 64/3 is the sum. And then we're going to multiply 40. And then we will actually get the right result. So basically, yeah. So this number going to be like, if you have 64 coins that add up, eventually is how many. Then basically, because we start from 64 pennies, so you basically divide this by 64, you actually will get this. Divide this number by 64 is actually, so expected, return for each penny going to be like 40, because this number divided by 64 is 40 divided by 3. It's still going to be 13 and 1/3. So basically, this is using the like more complicated way, which really consider each step by step, and calculate into, even you are able to break the coin into fractions. And so this infinite geometric sequence will turn out to be this type of the result. Okay, so we have more times for going to the, let's say that number theory. So let's try to go as far as possible on the number theory. So the number theory is mostly exclusively dealing with positive integer, and dealing with prime factorization, and also dealing with modular and unit digit, and relationship between decimal and fraction. So those are the topics we are going to go through. And the first is the sieve of the Eratosthenes. And so the way that you find the prime number, especially small range of prime number under like 100, like, thousands of years ago, this smart guy designed this way that, one, because it's not a prime, it's also not a composite, so it's not in consideration. So you list the numbers, and from the 2 is a prime, so it's labeled. Then for all the multiple of 2, so we colored it because those are composite. Then we also repeat for 3. 3 is a prime, and all the multiple of it is composite. then we do 5, and we do for 7. Then basically the whatever left over under 100, those are all the prime numbers, because you know because 100 square root is equal to 10. So in 100 is a perfect square. So for all the number below 100, you have to have a, if it could be factored, then the smaller factor will be less than 10. And for we only consider the prime factor, we only need to consider 2, 3, 5, 7, because all the other are composite. Then whatever are not multiple of 2, 3, 5, 7, those gray number basically are prime. So it's a very fast, efficient way, and a lot of computers using this as a homework. And so we also have divisibility rule, like if it is even, then divisible by 2, then divisible by 3 if it's sum of the digit, and divisible by 4 if the last 2 digits is divisible by 4. Divisible by 5 if the last digit either 5 or 0. Divisible by 6 if it's divisible by 2 and 3. And 7 has no good trick. 8 is the last 3 digit divisible by 8. 9 is the digit divisible by 9. 10 is the last digit in 1, and the 11 is at 11. Basically, the digital sum of the even position and the odd position, their difference is going to be 11 multiple. And so there are a lot of those problems. I'm kind of just going to show that how to fastly determine this. For example, which factor of this is this big number? So 2 is divisible. 3, how do we judge 3? Basically, if you find a 3, you just ignore it. You don't even to add. The trick is trying to add it up. But if one of the digits is already 3 multiple, so you don't count it. And 4, if it is a 3 multiple, you actually could use its remainder, because only the remainder really matters. So basically, so we don't count 3 because it's already 3 multiple. 3 and 4, we just count 1 because it's 1 extra one than 3. And this, we don't count it. And 5 is actually 2 more than 3. So you can add, say, 2, and 1 plus 2 equals 3. So those annihilate each other. So we don't have to add. In this way, basically, it's easier to count up. You don't really have to add any number. You just, when you reach 3, it clear to 0 again. So this basically, 8, you can even do it like -1. So basically, and then it's actually 6, you don't count it. And 4 is actually 1, and 1 and -1 will annihilate each other. So basically, when you do this, you don't really adding, you kind of just canceling or at very small number. You cancel them out at a number smaller than 3. So it between -2 all the way to 2. But when it reaches 3 or -3 or 0, then basically, it's kind of just cancel out. So we know that it's divisible by 3. And 4, it's divisible because that's 64, the last 2 digits. And 5, no. And 6, yes, because divisible by both 2 and 3. 8 actually is yes, because that's 864 is divisible by 8. And 9, we using the same trick, but this time we're going to use 9. So like, the easy part is that, if I find those 3 together, that's going to be add together to be like 10. And after you reach 10, it will go down to 1 because 10 minus 9 equal to 1. Or another way you can say 1 plus 0 equal to 1 because even the intermediate result, you still can use the addition of the digit to really reduce the size of the intermediate result to be a smaller number. For example, if we add to 10, then the 10 itself, we add a digit to get 1. So the first 3, we get 1. Then, um, and 1, actually, you can try to, if you find 1, you can actually try to find an 8 to really add up to 9. Then you don't have to keep both of them. Both of them annihilated. And also 8, you can actually treat it as a negative 1 because it's 1 short of 9. And then, so we annihilate 1, 2, 3, 5, or 4 numbers. And we going down for those 3 numbers. And those 3 numbers, 5 and 4 add up to 9. Those are annihilated. So the remaining is 6. So 6 is not divisible by 9. So it's not divisible by 9. And 8 already divisible, and 10 is not. So this is the way. Yeah. So for this type of the sequentially, added up number, for example, when we try to calculate 9, the best way is actually pair them. For example, if you can pair 1, 9, 2, 9, 3, 9, and the 4, 9, we know it's divisible by 9. So, um, so the divisible rule is a sum of the order digit, right? But I never really trying to add them together. I just, find the lowest possible number to cancel or round to 3 if it's 3, or cancel or round to 9 if goes to 9. Then it's much quicker to calculate. Yeah. So this problem is that what is the smallest 4-digit number that is divisible by 2, 3, 4, 5, 6, 8, 9, and 10. So basically what we are considering is a 4-digit number. And since it's divisible by 10, so the last digit has to be 0. So we already have a number, has to be fixed. Then basically, we need to make sure that these are the strict rules, like divisible by 8 and divisible by 9, because 0 already meet the 2 and the 5. So like 8 and 9 is, if you meet 8, you actually meet 4. If you meet 9, you also meet, both 3 and 6. So basically what we are trying to consider is that 8 and 9. So the first digit, we're trying to get the smallest possible position is 1. So we're trying to fit 1 to make sure that it works. Then otherwise, if the 1 do not work, we go up to 2. So 1, 0 is the thing we are trying to shoot for. And then because we have to add up to 9, and the smallest we want to do is that, because we go for the smallest, so if we can put 0 here, that's the most ideal. And then basically we put 8 because we have to make 9 by 1 plus 8. 8 is the smallest possible number we can get. Then we trying to, and this, because we already satisfied 9, then we trying to see if it satisfies 8. 8, we basically need to judge 3 digits. And those 3 digits actually divisible by 8. So actually this works. So this time the problem, the number theory problem, you just, find the priority and like 0 and this put 1 because we're trying to be as small as possible. Then this so is the 10, 0, and the 8. So that's the way that we can try to organize the problems. And the this problem is that use only 1 and 2 to make number divisible by 8. So number divisible by 8, basically, obviously, you know, the last digit has to be 2 because there's no way you can put a 1 over there. And then we will trying to check, you know, what is the last other 2 digit that are multiple of 8. And multiple of 8 and also multiple of 3. So it's very strict. And so we have to satisfy the 8 in the last 3 digit because that's the fixed rule. Then we will trying to satisfy divisible by 3 on the higher position. So that's our strategy. And then because we only have 1 and 2 on those positions, so this is fixed. So we only have 4 possibilities to mess with. So basically, it's actually 1, 1, 2, 1, 2, 2, and 2, 1, 2, and 2, 2, 2. So basically, and we figure out that, you know, this is the only one divisible by 8 because, you know, it's this basically 80 plus 32 and it's divisible by 8. And the other number, this is basically this is plus 10 and that's impossible. And these two also is not because we know that 240 is divisible by 8. And then basically, you know, this is actually minus 18. It wouldn't work. And this basically is minus 28. So this also do not work. So those 3 do not work. So 1, 2, 2 is the only way which you will make the last 3 digit divisible by 8. Then basically the total digital sum is actually equal to 4. So the next one, you know, possible to make, so 1, 2, 2, is actually 1, 1, 2. And the next digit, you know, we are too short of digital sum from 6. So basically the easiest one is put a 2 here. So basically that's going to be the number. I think so these problems are not very difficult. It's just, you know, you just have to find a priority to the digit of a number are all 8 and it is divisible by 9. What is the least possible integer that fits this description? So this basically each 8 basically contribute basically each 8 you can actually see it differently. Each 8 you can see it's a -1. Basically you can think about it as a -1 as modulo of 9. So basically, you know, when you add more 8 and -1 And 8, basically, it take 9, 8 to 9, 8 to add the -1 all the way to -9. So that will make it divisible. So basically, we actually have to use the like 9 of those. And another way to look at it is that 8 and 9 are coprime. Those are coprime. When you're dealing with the coprime number and another coprime number, in order for that coprime number, repeat itself to become a 9 multiple, the only way is, it has to multiply 9. So basically, it had 9 times it. So basically, for example, if you like all the digit is 7, you can change the 18 to all digit is 7. Then basically, how many one of them will repeating to, then it's still going to be 9 because those numbers are coprime. And then you are able to like check with 6. 6 and 9, those are not coprime. So basically, 6 already have a factor of the 3. So you only need to repeat 3 times. So you 6, 6, and 6. Because it already have a 3 as a factor. So you only need to make another 3 here. So it just need to have 3 to fit it. So basically, this actually works for like, if you're going to be 4, 5, 4, 3, you need only repeat 3 times, and 2, 2 and 1. So basically, 1, 2, 4, 5, 7, 8. Those all need to repeat 9 times because of coprime. And then only 3 and 6, you need to repeat 3 times to make it divisible by 9. Let's try to do the divisibility by 11. Let's try to reach the factor because those are actually easy topic. Let me try to be as fast as possible. So divisibility rule by 11 is actually, you can just adding and minus it because it's really the digital sum of the odd. For example, you add it up to be like 9 and the even is 9. So basically, another way you can actually add it. So this is, for example, this is 9 minus 8 plus 3 and plus minus 3 plus 5. So basically, if you do it this way, you can relatively keep the number smaller because you are canceling out around the way. For example, 9 minus 8 equal to 1. 1 plus 3 equal to 4. And 4 cannot cancel out 5. So this is not divisible by 9. So basically, you can either do it this way or you can cancel out ping pong this way. So there's a number theory reason behind this rule. I think we will talk about this later on in the later position. And then what we are doing is the factors. And So to determine a number, whether a number is a prime, we only need to check if this number is divisible by all the prime less than square root of n. Because if it has a bigger factor than square root of n, it's guaranteed to have a smaller factor that less than square root of n. So we only need to check the lesser one to find all. So that will reduce the calculation volume. And so even very big number, and so you don't really, for example, here, we know that 20 square equal to 40. So you only need to check all the prime number less than 20. You will be able to find out whether or not this is a prime or not. And for this, you can also gauge, for example, this is a relative big number. And we know that 25 square equal to 625. So you don't, if you check all the prime less than 25, you already should be settled on this number. And then we have the fundamental theorem of algebra. Fundamental theorem of arithmetic. Fundamental theorem of arithmetic basically is telling you that for any number, there's only one way to prime factorize it. Basically, after you prime factorize it, if you order the prime in the ascending order, then also put their index, put it into index format. There's only one way to really write the prime factorization. So this is the keyword, a unique prime factorization. And also the perfect square. The perfect square, the prime factorization of the perfect square, basically, it has to has the even index on every prime factor. This is the only way to be the perfect square. Then we talk about counting the number of the factors. Counting the number of the factor, basically, first we prime factorize it. So for example, here let's say that this number, let's say how many way to prime factor it, it's actually became a counting problem because there are 5 ways to choose the 3 index, because 3 actually goes from, the index of 3 goes from 0 all the way to 4, and the index of 5 goes from 0 all the way to 2. So we have 5 ways to choose prime factor 3's index, and we have 3 ways to choose prime factor 5 ways index. So basically, if we, how many ways you can factor this is actually 3 multiply 5 equal to 15. So that's kind of the way that, and so for a normal, for example, 40 basically we have 4 multiply 2 way, because that's 3 plus 1 equal to 4, 1 plus 1 equals 2. So we have 8 way. For any composite number other than perfect square, it's usually have like pair. It has the it has even number of factors. And only perfect square always has all number of factors. all number of the factors for perfect square. And why, you would ask? Because for perfect square, each prime factor always has even index. So the way we calculate the number of the index is to multiply index plus 1 on each position. So let's say index 1 plus 1. And if you have, for example, like k of prime base, then for each of those base, because the index is always even plus 1 equals odd. So basically, no matter how many one you have it's ik plus 1, because each I2 plus 1 and each I sub index is even. So you multiply it up, it's going to be odd. So for perfect square, it always have odd number of the factors. Positive factor, well, we are not counting the negative factors. If you count both positive and negative, it's always going to be even, because even for right now it's odd, but if you double the odd, it's going to be even, because the composite is already even, and if you add even to even, it's also going to be even. So this, we only counting the positive factors. So counting the factor, basically we are like prime factor first, then for each index, we don't care about the base, we just care about the index of each base, and we just add the index by 1 and multiply this plus 1 index as a string, then you will get the total number of the, yeah, the factor counting is just a very easy. So basically, this is just what I have been talking about. So this is 240 equal 2 to the 4th multiply 3 to the 1st multiply 5 to the 1st, have like, it's each index need to plus 1. Then you multiply it together, you got 20 factors. Then this is actually quite important. So if you know the total, then you are able to know whether or not you have a complete list of them, right? I think that's all for today. We're actually reaching a good breaking point. We know that, we have been going through, this is 4.2, and I will assign the homework. Have a nice one, everyone.我又怎么了吧？